So it's my great pleasure to introduce the first speaker, Kevin Zhang. Dr. Kevin Zhang currently serves as Senior Vice President of Business Development at Taiwan Semiconductor Manufacturing Corporation, where he's responsible for company-wide business strategy, including technology roadmap and customer engagement. He also co-leads TSMC's Overseas Operations Office, which is responsible for supporting the company's global expansion. Before joining TSMC in 2016, Dr. Zhang was Vice President of the Technology and Manufacturing Group and Director of Circuit Technology at Intel, where he was responsible for key process and design collaterals and co-definition and optimization for Intel products. Dr. Zhang has published more than 80 papers at the international conferences and technical journals. He holds 55 US patents in the field of integrated circuit technology. Dr. Zhang was the 2016 ISSCC Program Chair and served as the conference chair for 2021 and 2022. Dr. Zhang is a fellow of the IEEE. Please join me in welcoming Kevin Zhang.
Thanks, Frank. Thank you, Frank. Good morning, everyone. It's such an honor to be here to have the opportunity to share our view of semiconductor industry, present and the future. As Frank mentioned earlier, I'm a long-time member of ICCC community. I served the conference chair, virtual conference chair for 2 years during the pandemic. So I tell you today a little secret. I wish I will be remain to be the only virtual chair in ICCC history. My association with ICCC actually started over 25 years ago, so I'm showing my age now. So when I first attended the conference as a newly minted PhD, I remember I was totally in awe by the magnitude of the conference, the breadth, the depth, and the quality of the presentation. So I sit way back in the room, attentively listening to all the presentation. So today, I want to speak to all the students and the young engineer in the back. I'm the living testimony you can make all the way up here. But take a lot of hard work and some gray hairs. So let's talk about semiconductor today. We all know life runs on semiconductor. Semiconductor truly has become the foundation for the modern economy, right? Anything we do rely on semiconductor. I bet everybody has different semiconductor in your pocket right at the moment. So from high-performance computing, AI, machine learning, to communication, from transportation to healthcare, you name it, everything depends on semiconductor. Since I'm wearing business hat these days, so I want to talk semiconductor a little bit from business perspective. As you can see today, worldwide semiconductor revenue is about 500 billion, $500 billion. So it's a common consensus. By the end of this decade, this number will double. But I have to add a qualifier here, given the recent surge of AI. The $1 trillion number does not reflect the multi-trillion dollar Sam Altman of OpenAI plan to invest in semiconductor. It doesn't reflect the latest projection from Lisa Su of AMD talking about a $400 billion AI market alone by 2028. It's bigger than iPhone. I think nobody knows exactly how the AI is going to shape this growth curve. But one thing is certain. We are entering an accelerated growth period for semiconductor going forward. If you take a little bit deeper look on this potentially $1 trillion market, high-performance computing, HPC, take the top position, equaling 40%, equaling the mobile combined with IoT. Just a few years ago, this is unthinkable because the conventional wisdom always believed it's the edge device where you consume the most silicon. But no more, thanks for the surge of AI. Talk about the AI, I have to talk about ChatGPT. Since the introduction of ChatGPT over a year and a half ago, we're already seeing the landscape is changing in the semiconductor industry. If you look at this steep curve, what behind this steep curve is really the insatiable demand for energy-efficient compute. So Jensen Huang, NVIDIA CEO, said, ChatGPT is the iPhone moment for AI. Sam Altman of OpenAI said, the new Moore's law is AI. The total intelligence in the universe get doubled every 18 months. You can describe AI in different way, but one thing is for sure, it requires a lot of advanced semiconductor, more than everybody can imagine today. Talk a little bit about communication, wireless communication. This is very important in our life. Here, I show you 3 connectivity technology, from cellular to Wi-Fi to Bluetooth. As you can see, all the advanced standards require a higher data rate, more advanced signal processing. This will continue to drive the accelerated adoption of advanced silicon technology. Using Wi-Fi 7 as an example, actually this year, we're moving into the production of Wi-Fi 7. From the get-go, Wi-Fi 7 has to adopt 7-nanometer technology in order to achieve the power performance targets. I want to talk a little bit about automotive. Automotive is really going through a fundamental revolution. Lots of people call the new automotive will be software-defined automotive. But I think the better term is a silicon-defined automotive. The reason is being software has to run through on silicon. And you see there are lots of silicon, right? From sensor, connectivity, network, and to most advanced semiconductor technology to drive the autonomous capability going forward. Before I dive into the technology discussion, I want to take a moment to talk about the business innovation of semiconductor industry, the introduction and the pure play foundry model. This is pioneered by Dr. Morris Chang over 3 decades ago. This innovation has fundamentally changed the landscape of semiconductor industry. By taking out the very complex, costly technology manufacturing out of the traditional IDM model, allow the IC company focus on their product development, focus their innovation. By working together with the foundry, actually we greatly together accelerate the innovation in the whole industry. Because of the introduction of the foundry, there are lots of new players occurred, and the fabless company flourished. As fast forward to 2030, as you can see, over 50% of the semiconductor revenue will be contributed by the fabless company, the system company, or cloud provider. That's all because of the business innovation, the emergence of the foundry. So now let's talk about the technology. Transistor remain at the heart of the innovation, silicon innovation. The transistor has gone through a significant evolution over a few decades since it was invented over 75 years ago. So as you can see, in the early days, transistor innovation largely centered around the geometry reduction, but that's no longer the case. In recent generation, it's all focusing on the innovation in the transistor architecture and the use of a new material. For example, the 16 nanometer will move from planar transistor to the FinFET transistor. And today, we're at the dawn of introduce a brand new transistor architecture, 2 nanometer, called nanosheet. By wrap around the entire channel with a gate control, you actually greatly improve the electrostatics of device, improve the conduction, and provide a better capability to operate at an even lower voltage. This is very, very important for high-performance computing. Talk about the patterning technology. The introduction of the EUV at the 7 nanometer actually paved the way for us to continue drive the geometry scaling going forward. So you may ask, what's the next? I would say first thing first, actually, we need to milk this nanosheet transistor for a couple of generations to extract the best value, the maximum value after this new transistor architecture. But at the same time, our technology is already busy at making a brand new transistor architecture. Here I show you one promising example called CFET. Essentially, by stack the N transistor, NMOS, and the PMOS on top of each other, you can greatly improve the density by nearly a factor of 2. And on the material front, our technologists continue to work on the new material, like a low-dimensional material. By introducing this new material, we think we can achieve even more energy-efficient switching devices well beyond today's device or transistors. This is a little bit further look at what the benefit the CFET can bring to you. As you can see in the logic gates, like an inverter, you can stack N devices on P device. Same thing can be applied to the 6T SRAM cell. In doing so, you get nearly 2x of the density enhancement. Very, very significant. This is no longer a simple idea on the PowerPoint. Actually, here I want to show you a TEM picture. This is a real integrated device has been fabricated in our lab. And you show here you see the transistor IV curve. They're beautiful curves. So this is a significant milestone in terms of continue to drive the innovation of the transistor architecture. As we shrink the geometry of the transistor, it's getting harder and more costly. Designer and the technologists have to work together in order to achieve optimum scaling benefit at the product level. So we often refer this as called design technology co-optimization, or DTCO. Here I show you one example in the digital library design on the FinFET technology. By using so-called technique called depop, reduce the number of fin per cell, you actually can reduce higher the cell, reduce the geometry, and at the same time lower the power consumption. But when you reach the 2 fin per device, the designer faces a difficult time or dilemma. If you go further, you will pay a severe penalty in the speed. By DTCO, by innovation, actually our design and technology team work together to come out with this new idea we call FinFlex. Essentially allow designer to mix and match single fin devices, 2 fin devices, or 2 fin versus 3 fin. So we can achieve optimum performance, density, and the power consumption at the same times. Talk about the DTCO. Another good example is really about the SRAM bit cell. Here I show you the SRAM scaling from 130 nanometer all the way to today's 3 nanometer. We achieve over 100x density improvement. This scaling is really the result of collaboration or combination of a process innovation and adoption of the more advanced design technique. I don't know how to partition who has done how much, but I often tell my folks, technologists and the designer, you are just equally important. Yeah. Talk about the SRAM, you have to talk about the minimum operating voltage, or Vmin. In the good old days, in order to lower the voltage, you have to adopt a larger memory cell. But let's know more. By applying innovative design technique, in this case, like a negative baseline write assistant technique, you actually can achieve over 300 millivolt Vmin improvement. This is very significant for low power operation. So I talk a lot about technology scaling. The essence or the objective of this technology scaling, in the end, is really come down to this, the energy efficient compute. So the industry as a whole, we come a long way. Here I show you the scaling. Just over a little bit of decade, we achieve over 80x energy efficiency. This kind of advancement really enable today's emergence of AI. So people in this room should be very proud of how far we have come along. So let's talk a little bit more about technology platform for HPC or AI. If you look at today's, all the so-called AI accelerator, whether it's GPU, whether it's TPU, or customized ASIC, all essentially feature this particular integration scheme. Basically, you use a CoWoS chip on wafer on substrate, bring the advanced piece of silicon, today mostly 5 nanometer technology, and the high bandwidth memory together. But this is not sufficient. Going forward, this platform needs a significant uplifting to address the future high-performance computing needs. So in the heart of this configuration here is really higher density, low energy compute. So you need to go to stack in order to achieve computation density. So you need to stack vertically multiple most advanced silicon pieces together to provide the computation density required. And you need a lot of memory bandwidth. So you need to bring more HBM into the package. So the interposer or CoWoS has to expand further in order to comprehend this. But that's still not enough. The power delivery is a problem. So you need to integrate the voltage regulator in order to solve the power delivery challenge. And I/O and the bandwidth interconnect density become an issue too. So for that, you need to bring silicon photonics into the package. So this is where the future is going. There are still lots of challenges in order to bring, for example, the co-packaged optics closer to the electronics die. But the physics tell us this is the future. So let me talk a little bit more about the 3D stacking. Here I show you the interconnect density. Because stacking, the reason we go stacking is really to achieve high interconnect density or chip-to-chip communication. These two curves show the top is SoC, essentially it's a monolithic interconnect density. The bottom is a conventional packaging density you can achieve. The middle, obviously, is a CoWoS, which is often used the 2.5D solution. But going to 3D solution, we call SoC solution. By doing that, by aggressively scale the bonding path pitch all the way down to a couple micron range, you actually can achieve the interconnect density like monolithic. That's why the 3D is the future. Let's also talk a little bit about the silicon photonics or co-packaged optics for the future high-performance computing. We know electron is very good at the computation, but photon is better when you come to the signaling or the communication. Here I use a 50 terabit switch as an example. Everything is electron. It's a copper system. This system will burn up to 2,400 watts. Today's solution is you convert photon at the board level by using so-called pluggable optical transceiver. You actually can reduce power by 40%. But this is not sufficient. The future requires more high-speed signaling, more bandwidth. So in the future, you need to convert electrons to photon much earlier inside the package. So you need to bring the photon capability right using the advanced packaging technology we call co-packaged optics. In this particular case, you have to also leverage advanced stacking to bring the photonic die and the electronic die together. By doing so, you can cut down the power consumption by 50%, achieve roughly about 5 picojoule per bit. So this is where the future is going. So today, using most advanced transistor technology, you can pack roughly about 100 billion transistors in the same die. I'm not talking about small die, I'm talking about pretty big die. But this is not sufficient to address the future AI machine learning application. You have to leverage the advanced packaging 3D technology to really pump up the number of transistors to trillion transistors to address the future computation need. I want to talk a little about the cellular RF. I remember when I was chairing memory subcommittee at CC, I was always jealous about how many big audience RF paper can always draw. So I do pretend to be an RF person, talk a few things about RF from technology perspective. So let's go back the 4G to 5G transition. In order to improve the data rate by tenfold, you need to incorporate lots of more digital circuitry, like advanced ADC, advanced signal processing capability. So in doing so, RF transceiver design actually can benefit greatly about moving from 28 nanometer to 16 nanometer back to 4G to 5G transition. But if you look forward, 6G, for example, you need to cover broader range of the frequency. like a FR3, you need to pump up the data rate another tenfold. So this will require even more advanced semiconductor, more advanced computation technology. So you would not be surprised to see the transceiver, future transceiver design will base on 7 nanometer or even 5 nanometer. I want to talk a little bit about automotive. Automotive is a very, very exciting area. If you look at deeper on the automotive, fundamentally it's really bring lots of computation power into your car to support less autonomous driving. Today, we're really at the beginning, right? In order to achieve, I call it the eye off, minds off, you really need over thousands tops in a car. But the power consumption is becoming a real problem, especially for battery-powered car. One of my friends working in a leading auto OEM tells me he's the most hated guy in this company because all the other guys push hard to save every bit of energy to let car run a few extra miles. But when he bring more powerful SoC design, more powerful, I mean it's literally more powerful. So it wipe out all the gain the other guy have done. So I told him, hey, you need to go to advanced silicon technology. How about the 5 nanometer, 3 nanometer? Not so fast, not so fast. There is a good reason why the silicon technology for auto has always stayed back a couple of generations behind the consumer or HPC. That's because very stringent safety requirement. The defect density requirement for auto application is basically near 0 DPPM. To achieve that level of DPPM, you need run millions of wafers for years to achieve that level of defect density. But that's not fast enough to address the future automotive requirement. So foundry, semiconductor manufacturing, and the auto design folks have to work more closely going forward to accelerate that pace. A couple of things we're doing. For example, we apply auto design rule upfront to reduce the defect density. And we're applying, at time zero, applying more intelligent dynamic voltage stressing to basically screen up the potential defects part and provide fast feedback on this failure analysis. So in doing so, now I see clear paths we can accelerate the adoption of more advanced silicon technology for auto application. So here I'm speaking to my favorite crowd. So it's my commitment to all of you. You will see 3 nanometer in your car before long. So talk about automotive silicon technology, I have to talk a little bit about MCU, which featured embedded non-volatile memory. This is very important. MCU become more important as auto transitioning to the zonal architecture, where you really need advanced silicon technology to provide computation power for MCU. The traditional MCU largely feature the floating gate-based technology, but floating gate scaling at 28 nanometer run into the wall. It takes 18 masks to integrate the floating gate cell into the logic technology. That clearly is not viable going forward. The good thing is the industry has invested in this new memory technology we usually call emerging memory technology like magnetic RAM or resist RAM, RRAM. It turned out that this emerging memory actually emerged in time to intercept the future MCU technology. So by moving the MCU to MRAM-based, RRAM-based technology, actually you can see we can continue to drive the technology scaling, quickly go down from 28 to 16 and the future to 7 nanometer. So I want to talk a little bit about sensor and display. We always say, logic technology is the center of this digital transformation. But the world we live in is analog. The physical world is analog. So sensor and the display technology play an essential role in bridging the real world and the digital world. So the integration of digital camera with the smartphone actually fundamentally changed how we document and communicate our life. As you can see, over 1 trillion pictures being taken now per year. It's very important technology. The sensing technology has evolved substantially over the years. From simple two-dimensional design, single-layer design, now we have this smart system based on 3D wafer stacking. Basically, you stack the signal processor layer wafer on top of the sensing layer. Going forward, our technologists already start investing, researching on the multi-layer design. The reason doing this, I'll show you a couple of examples. For the pixel optimization, one of the key benefits by doing 3-layer or more layer design is you can split the photodie and the transistor into different layers. So you can optimize the pixel without shrinking the photon collection volume. Efficiency is very important. Then you move the transistor on the other layer. So this is where we can continue to drive the pixel scaling to achieve the resolution requirement, but same time achieve optimum sensing capability. Another good example on this multi-layer sensing approach is for AR/VR, where the form factor is a paramount requirement. So by splitting the storage of the different layer and stack on the rest of the logic, you can effectively shrink the geometry at the same time maintain the high performance requirements. So now, I would like to conclude my talk by looping back to the economics of semiconductor. We talk about this $1 trillion market by 2030. If you really want to size up the impact of this $1 trillion semiconductor, you have to consider the multiplication effect. This 1 trillion transistor semiconductor drive up to 3 trillion electronics industry and generate 12 trillion IT revenue and create over 145 trillion GDP. So economic impact from semiconductor is enormous. I want to share a little bit personal anecdote with you. 7 years ago, I left then the largest semiconductor company, went to Taiwan. At that time, I was thinking my best time in semiconductor has behind me. So I just going to Asia, sunset my career. But fast forward 7 years later, instead of seeing sunset, I see a bright sunrise. With emergence of AI, semiconductor is going to power so many new applications. It's going to touch every aspect of human life and change the trajectory of the human history. So I see a bright golden era right in front of us. There is never better time to be in semiconductor industry. Our best day still ahead of us. Let's work together to make it happen. Thank you for your attention.